Adjustments and corrections of measurements for satellite navigation are generally well understood by navigation professionals, but one, Earth rotation, has presented a paradox even to some highly qualified experts. This video will briefly summarize the set of adjustments with emphasis on that paradoxical effect. The true reason why it's there will promptly resolve the issue. Pseudo-range and carrier phase are composed of distance from satellite to receiver with various adjustments, for example, bias, clock effects, in addition to propagation effects. Both measurements can be defined in a common expression when certain underlying interpretations are understood to apply. Propagation adjustment includes both tropospheric and ionospheric corrections, for example, but the algebraic sign for iono depends on which observable is being formed. Also, the satellite clock correction is defined to include the relativistic effect. With that understanding, and with the usual integer plus fractional wavelength subdivision of carrier phase, the value at time of measurement index m for satellite index j can be expressed as equation 258 of GNSS-aided navigation and tracking. It looks like this, where subscripts J and U refer to transmitter and receiver, respectively. Much of the interpretation was just summarily expressed, but Earth rotation, chosen to be implicit rather than explicit in this equation, calls for further clarification. I'll postpone that until the end here, in order to mutate from the compact form of the above equation towards something more instructional for those not already familiar. The beginning will go back over what was already stated a little more slowly. The first chapter of the book just cited explains heavy reliance on references including a much earlier 1976 book for basic Kalman filtering plus inertial nav, and three widely known sources for satellite navigation. If I had it to do over again, I might have made that reliance less complete and sacrificed brevity to include more introductory details from those sources. A mountain of documented research would, of course, preclude anything approaching thoroughness, but this video can fill in some of the details, with no attempt to cover detailed compensation methods, likewise extensive. Adjustments will begin with ionospheric propagation and continue in the order of appearance in the equation just given. All descriptions of them came from other authors, for example, those who wrote material in the three widely known sources for SatNav. Ionospheric propagation advances the carrier phase while delaying the envelope code of the signal in space waveform. Much of the extensive research devoted to it is focused on total electron content, TEC, which is actually an electron density that varies substantially with time, for example, due to solar influence, and location. The resulting amount of lag or advance is directly proportional to TEC, inversely proportional to carrier frequency squared, and also dependent on above-horizon elevation of the receiver to SV sightline. A lower elevation angle makes the signal in space travel through more of the ionospheric medium. Tropospheric propagation delays both carrier and code. An increased amount for lower receiver to SV sightline above horizon elevation angles is again true of a tropospheric delay, and the effect also increases at lower altitude for a similar reason. There is a further dependence on moisture along the signal in space path, for example, presence or absence of waterways below. Receiver bias arises from delay within user equipment, signal travel through waveguides, front end, etc. Characterization is direct and essentially self-explanatory. User clock offset is dealt with either through elimination by subtracting synchronized measurements from SV pairs, or, unlike the other adjustment terms, as part of the nav solution. As defined above, SV clock offset includes the sum of a correction encompassing effects of special and general relativity plus a quadratic polynomial. The relativistic component is computed from a standard equation, universally accepted, and the polynomial coefficients are obtained from the nav message superimposed on the signal in space code modulation. Although my program places the relativistic effect with the satellite clock correction, it could have been omitted for the dynamics segment, where 1 second changes in carrier phase are formed in the book cited earlier, but not in the position segment, which forms differences across satellites but not sequentially. Earth rotation now comes to the center of attention. It is often expressed as a separately identified additive term in the measurement equation, set equal to the long-range, SV to receiver, component of the receiver's motion during the signal in space transit time. Here's the paradox. Literal interpretation in that form would violate Einstein's theory of special relativity. Motion during transit time cannot change the speed of electromagnetic transmission. The issue is not resolved by acceleration that accompanies rotation, separating this phenomenon from the realm of special relativity. Motion during the brief transit time is, for practical purposes, constant speed along a straight line. Immediate resolution of the issue stems from the expression for unadjusted magnitude of the vector difference. Vectors to be subtracted must be expressed in the same coordinate frame. Both are readily expressible in ECEF, Earth-centered, Earth-fixed, but are tagged at different times. Instantaneous receiver location is evaluated at the time of reception, whereas for satellite measurements, SV position must be defined at the time of transmission. During transit, the ECEF frame rotates about the geodetic pole through an angle equal to the product sidereal rate times transit time. The effect of this rotation produces that component of receiver excursion along the direction from the satellite to the receiver. If a more thorough description for that effect ever became necessary, discussion following equation 565 of the 2007 book cited earlier provides it.